Believe it or not, but there is still a significant debate about what is a system. Strangely, after millennia of dealing with such things, it's hard to find even two people who have a common view on what constitutes a system, which is not terribly useful when we're trying to communicate without misunderstanding. And that's particularly important if we're trying to share a common view of a system when we're considering a discipline such as systems engineering. Now, the variation in the use of the word system means that perhaps it's one of the most overused words in the English language, even to the point where you could probably replace system with stuff and not lose much meaning. And that's because the word system has many contexts. There are physical systems such as solar systems, river systems, railway systems, satellite systems, communication systems, information systems, pulley systems, nervous systems, just to name a few. And then there are conceptual systems, such as philosophical systems, social systems, religious systems, gambling systems, banking systems, systems of government, and many, many more. The word is even used for more esoteric examples, such as the consideration of individual and social behaviour as a system of purposeful events. Now, in all these contexts, the common aspect of the use of the word system comes from its early meaning and its Greek root. A system refers to the whole, or the set, that results when a number of things have been grouped together, in a particular manner and for a particular reason. What the set is, how it's grouped, and for what reason, is context dependent, however. So before we continue, we should briefly consider what we mean by a system in the particular context of systems engineering. In systems engineering, a system can be defined as a set of elements that interact to achieve a stated purpose. This definition implies that a system comprises system elements with interconnections or interactions between those elements, and by the very act of identifying the system that we're interested in, an external system boundary is also implied. When we draw the boundary around selected system elements, we define the system of interest. That system of interest comprises those system elements and their interconnections that exist within our defined system boundary. The purpose of the system is called its mission, which must be clearly stated by business management and stakeholders. The mission represents the start point for the design process, as well as providing the basis for the ultimate test of the system's fitness for purpose once it's been fielded. In the broadest sense, then, the mission of the system is to provide a solution to a business problem. This narrowing of the general use of the word system is very important because it has two major implications. First, when we refer to a system as comprising system elements that are interconnected in order to achieve a purpose, we imply that all three of those principal aspects result from conscious choice. That is, we're referring to a system that has been deliberately designed or engineered, hence our interest in systems engineering. A system that has been engineered to perform a specified mission must be able to perform that mission with relative autonomy. That is, it must be managerially and operationally independent, and it may well have even been procured independently. We return to this issue shortly when we discuss the difference between systems and subsystems and between systems and systems of systems. There are numerous ways to classify systems. Here we identify the four main types in order to be clear as to which type of system we refer to in systems engineering, and therefore in the remainder of this course. There are closed or open systems. There are natural, human-made or human-modified systems. There are physical or conceptual systems. There are precedented or unprecedented systems. Let's look at each of those a little more closely. An open system interacts with its operating environment. That is, it's open. It accepts inputs from that environment across its boundary and returns outputs across the same boundary back into its external environment. A closed system, on the other hand, is isolated from its external environment. We are only interested in useful systems, which must therefore be open. Natural systems contain natural elements and are the result of natural processes. Human-made systems come into existence through the efforts of humans and may contain some human-made elements or perhaps some natural elements adapted to human-designed purposes. Natural systems that have been modified for human purposes are called human-modified systems. The The systems engineering for natural systems has certainly not been conducted by humans, so we are only interested in human-made or human-modified systems. Physical systems exist in a physical form. Conceptual systems do not, they're conceptual. Since our focus in systems engineering is on engineering a system, things we can actually produce, we're interested in physical systems. In a precedented system, similar such systems, or at least the majority of system elements, have been produced before. An unprecedented system is one that's not been previously produced. Systems that comprise mostly unprecedented elements are the result of research and development. Here we're focusing on systems that comprise largely precedented elements, that is, those that we have engineered before, and therefore those to which systems engineering is most appropriate. Now, based on those four classes of system, there are a wide variety of combinations that can lead to a large number of types of systems, each of which has markedly different properties. But it's important to recognise that in this course, and in systems engineering, we're talking about open, physical systems that are human-made or modified from largely precedented elements. Now, returning to our simple diagram of a system. Since we're interested in engineering physical systems that are open, our system of interest must accommodate external interfaces, that is, inputs and outputs, across the system boundary, connected then to external elements that exist in an external operating environment, or perhaps a related system. To extend even further, sometimes we need to be aware of an even wider context. So an SOI might be considered as part of a wider SOI, a WSOI, which exists within an operating environment. And that operating environment could be conceived to even be part of a wider environment. In a physical sense, the term system is sometimes considered to be synonymous with product. That is, we say that the project is delivering a system or it's delivering a product. A system, however, is normally considered to comprise a number of products. NCEIA 632 sees a system as comprising operational products, or end products, and enabling products, such as test, training, and disposal products. Before we go any further, however, we must acknowledge that the systems we are interested in are much more than an aggregation of hardware or software products, and must also be described in terms of all of the constituent elements, including the major hardware and software, of course, but also the organisations within which the system will be fielded, the personnel who will interact with it in many ways, the collective training systems required, as well as the facilities, the data, the support, including even supplies, required to keep the system in service, as well as the operating procedures and organisational policies. The system is fully defined by the combination of these resources operating in its operating environment in order to achieve its purpose, its mission. In that sense, then, we can define a system as delivering an operational capability. It's common, therefore, particularly in defence environments, to refer to the system at this level as a capability system. In the US Department of Defence, the acronym DOT-MLPF refers to the capability system elements of doctrine, organisation, training, materiel, leadership, personnel and facilities. In Australia, the capability system is considered to comprise fundamental inputs to capability, or FIC, command and management, organisation, collective training, major systems, personnel, facilities, supply and support. In the United Kingdom, the defence lines of development refer to doctrine and concepts, organisation, training, equipment, personnel, infrastructure, logistics and information. In Canada, the acronym PRECEDENTED refers to personnel, research and development, infrastructure, concepts and doctrine, information technology and equipment. And all of these acronyms refer to a system as a capability system. Now, having acknowledged, therefore, that a capability system has a number of elements, it must also be recognised that each of those elements will probably have a different acquisition cycle. For example, people will be acquired in a different manner to that in which the major system was developed. And each element of the capability may even be acquired by a different acquisition element of the organisation. Consequently, joining all these subsystems together into a system is actually a complicated effort. In the remainder of this course, for ease of description, we focus on the acquisition of just the major equipment element, often called the material system, to make it easier to understand the linear sequential process. We must always keep in mind, however, that this acquisition is being undertaken in parallel with the acquisitions of the other elements of capability, and that all of those elements must then be brought back together prior to introduction into service in order to field the full operational capability. So, for example, in an aircraft system, the resources for that capability system are many. They will include, but not necessarily be limited to, the people we need, so the personnel. We need aircrew to operate the system and ground crew to maintain and support the fleet. We need support. We need maintenance facilities and equipment for routine maintenance and repairs. Materials are required to operate the system, including the fuel, of course, and lubricants and other consumables such as tyres and spare parts. We need facilities for support and for operations. We need terminals and support facilities to maintain the aircraft. We need organisations and policies and procedures. ACME, the company that runs the aircraft, will need to conform to a significant number of regulations and will need appropriate organisational structures, policies and procedures to operate the aircraft effectively. We'll need collective training systems. The aircrew and the ground crew will require training throughout the system lifecycle. We'll need data. Data is required to maintain and operate the aircraft, and also to include maintenance information such as specifications and drawings, and operational information such as user manuals and instructions. But then finally, of course last but not least, we need the major equipment. We need the aircraft. The aircraft will need to be produced and then deployed to those operators who will use the aircraft in a number of different ways, and of course one of those users will be ACME. Of course, there is much more to major equipment than hardware. Software is also now a critical item within many systems. The aircraft will use hardware and software to control a range of functions from engine management through navigation and environmental control, communications and flight control systems. A system can be described in two broad ways, in logical terms and in physical terms. A logical description, historically we've often called that a functional description, articulates what the system will do, how well it will do it, how it will be tested, under what conditions it will perform, and what other systems will be involved with its operation. A physical description relates to the system elements themselves. It explains what those elements are, how they look, how they'll be manufactured, how they'll be integrated, and how they'll be tested. So a logical description is about what, and a physical description is about how. But both those descriptions, of course, are very important, and they both exist together. And both of them require what we call later a series of statements called requirements. Now, the two descriptions are valid, independent descriptions of the system, and it's very important that the system is described both logically and physically. But of course, we must focus first on the logical description. Now, in one sense, it's axiomatic that we develop that logical description first, in order to determine whether any particular physical system is appropriate, that is, how we're going to do it is useful to us. We must first understand, of course, what it is we want to do. What purpose do we want the system to serve? We therefore need to focus on the logical description, the what, before we examine a series of candidate physical descriptions, the hows, of how we might develop the system. One of which, of course, is going to be chosen as our preferred physical solution. The second reason is we must also not allow the way in which we currently implement current systems to colour unnecessarily the way in which we describe future systems. If we focus on the logical description, we can then focus on perhaps novel solutions to new or even old problems. If we focus on the physical solution first, we would always end up solving new problems with the old physical building blocks. Third, if we're going to trade things off, if we're going to actually trade off value for money, for example, then we need to do that at a logical level before deciding on the physical implementation. If not, we may waste significant effort selecting physical solutions which either perform unnecessary functions or don't perform something which actually is critical. Next, a logical description is ideally suited to the interface between systems engineering and the business case. While it's often possible for the business case to be met directly by an obvious physical solution, it's probably better for business management to transition from their business case into a more detailed logical description before going on to deciding how to solve that problem in a physical sense. The definition of the logical description before the development of a physical system therefore moves from the business case to the final solution in a more controlled, more verifiable way. And the final reason is that the logical description changes much more slowly. The physical description changes very quickly, particularly these days with changes in technology. Arguably, for example, the need for and the upper level description of an internal combustion engine hasn't changed much over the last 2 centuries. Its purpose is to provide forward motion for the car. But the physical implementation for an engine has changed dramatically. That is, the purpose of the system as part of the car hasn't changed, but the way in which we do it has, as we avail ourselves of new technology. In the development of a system, therefore, there are the 2 architectural views, a system logical architecture and a system physical architecture. Now, of course, these 2 descriptions are of the same system, so they must be related. We'll see later how the logical architecture, as outlined in the requirements breakdown structure, is mapped onto the physical architecture as it's represented in what we call the work breakdown structure. We saw earlier that a system can be defined as the combination of system elements which interact to achieve a defined mission. Now, since each of these system elements will need to perform functions that have been allocated to it so it can contribute to the system's mission, we can consider a system to be a hierarchical composition of system elements. In a logical description of a system, the system's mission is broken down into a hierarchical structure of its major functions. The logical description or architecture is therefore often called a functional hierarchy or a functional architecture. In a physical sense, we saw earlier that a system can be considered to comprise operational or end products and enabling products. The end products of the system are also normally described in a hierarchy. Here we use a simple 4-layer hierarchy. We can say that the top level thing is the system, and it comprises subsystems, each of which comprise a number of assemblies, each of which comprise a number of components. And this then forms a physical hierarchy of the system. There are other terms in use, but these are probably the most common. The application of these terms to specific situations and different examples also depends very much on the context of the situation and where within the overall project the system is being considered. For example, if we take the highest level of an aircraft system, we could consider that an aircraft contains, amongst other things, an engine subsystem, and that would comprise assemblies such as fuel tanks, pumps and lines, turbines, compressors, gearbox and hydraulic pumps and so on. Now, from the viewpoint of an engine manufacturer, however, the engine could be considered to be a system, and it comprises fuel, power plant, hydraulic subsystems and so on. The problem is, however, if we consider the engine subsystem to be a system in its own right, an implicit part of the definition of a system is it has to be able to stand on its own. By that definition, an engine is not able to be considered a system. It's only useful as an element of a system, that is, as a subsystem. It's probably better, therefore, to consider a system of interest to comprise a combination of interacting system elements, some of which may be systems in their own right. When the system of interest consists of only system elements that are systems in their own right, the system of interest is called a system of systems. Now, a system of systems has a similar architecture to that of a system. That is, both comprise elements that are interconnected. But there is a difference. And the difference is that the system of system elements are systems in their own right, so that they're managerially independent and operationally independent, and have probably been optimized for their own purposes before contributing to the purpose or the mission of the system of systems. Now, on the other hand, if we take the system, the subsystems in a system are not independent and only exist to serve the parent system. Subsystems are therefore invariably not optimal from their own perspective. That is, they could be better. But it's the system that needs to be optimized, not the subsystems. We'll return to this issue later. The distinction between systems as element of a system of systems and subsystems as elements of a system is therefore that the system of system comprises systems that have been optimized for their own purposes before joining the system of systems. On the other hand, a system comprises elements, the subsystems, that are not optimized for their own purpose, but have been optimized for the system's purpose. From the higher level perspective then, a system of systems is most likely not optimised because the elements, the systems, were first optimised for their own purpose before joining that system of systems. Now, system of systems and systems, the distinction becomes quite blurred. So in this course, we'll leave it alone. We're focusing on systems whose elements are all subsystems, systems that are systems genuinely in their own right. We can complete our introduction to the nature of systems by returning to one of the early observations that a system can be considered to be the solution of a problem. As well as viewing the system descriptions in logical and physical terms, therefore, it's common to consider the activities being undertaken throughout the life of the system to be either in the problem domain, the problem space, where we use mainly logical descriptions, or the solution domain, or the solution space, where we use mainly physical descriptions. We'll see later that the activities in the problem domain, including the production of the logical architecture, are mostly the responsibility of the customer or the business owner. The solution domain, including the development of the physical architecture and the physical solution, are generally considered to be the responsibility of the organisation who's developing the system, and we call them the developer. So, the aim of this presentation was to identify what we mean by a system, particularly in the context of systems engineering, and particularly as a shared understanding of the nature of a system, which is essential if we're to progress with a shared understanding of the systems engineering discipline. Well, if you're interested in this and similar topics, you may also be interested in the Capability Systems Centre at UNSW Canberra. The centre is an independent think tank that offers cutting-edge research and analysis to government, defence and to industry. If you are after more information, please visit our website. You may also be interested in these two texts, System Engineering Practice and Requirements Practice. Both are available in paperback form from the Amazon websites or the publisher Argos Press websites.